All right, so in linear, you have two things bonded to the center and no lone pairs. These can be a single bond, a double bond, or a triple bond. And you're going to have a central atom and two things attached. Now, in a linear molecule, the only domain or the only geometry that you can make is linear. So you have your center atom, and then you have your two things bonded to it. There is no other shortened version. All the bonding domains are going to be filled with a pair of shared electrons, and so the molecular geometry here would be linear. So in a correct description of what shape this is for both the electron domain geometry, you're going to say linear, and the molecular geometry would be linear also. When it comes time to look at the electron domain geometry of trigonal planar, now remember this would be, typically this is three things bonded to the center and one lone pair, and this can be a single bond or a double bond as well. You can have multiple versions of this bond domain geometry. You can have your trigonal planar, which has your center atom and your three things bonded. And in this case, we have all the bond domains filled with pairs of electrons. And so that one is called trigonal planar. So both the electron domain and the molecular geometry would have the same name. Now, the second version would be when you take away one of those bonds and you replace it with a lone pair of electrons. So we draw in two of our bonds, and this one we have two electrons in. Now this one we recognize as two things, this isn't three. This is two things bonded and one lone pair, and this one is called bent. So when you're describing this particular bent, the electron domain geometry is trigonal planar, but the molecular geometry is bent. So this bent here is part of the trigonal planar geometry family, if you will. When you get around to tetrahedral, there are three possible geometries that you can form. You have your tetrahedral, which has your central atom and your three bonds around the center. All right, so the next version would be your central atom, and you still have your three around the center, but in the one place where you had a bond pair, you've now replaced it with a lone pair of electrons. And so in this case, this one has three bonds and one lone pair, and we recognize that one to be triangular pyramidal. So in this case, this would be the electron domain tetrahedral, but the molecular geometry trigonal pyramidal, triangular pyramidal, either way. The third version of tetrahedral electron domain would be the other bent. So you have your center atom, and you have your two bonded atoms, and then you have your non-bonding pairs placed, and this one is bent. So we had a previous bent on the other screen, and that was part of the trigonal planar electron domain. But this bent, because it has four potential locations for bonds, is part of the tetrahedral family, and it has the specific molecular geometry of bent. Okay, so in trigonal bipyramidal, remember that we have an expanded octet here. We have 10 electron pairs around our center atom. And in the trigonal bipyramidal molecular geometry, you have your two connected and then three around the center. We've used words to describe this shape as axial and equatorial. Axial are in the upright position, and equatorial are in the position around the center. So in the case where you have all 5 bond domains filled with bonding pair electrons, that one is called triangular bipyramidal with a molecular geometry of triangular bipyramidal. You can also then go on and have additional lone pair electrons attached, and they will have successively different molecular geometries. So if we go back and we try to represent our 4-in-1 here, I'm building it and thinking and talking all at the same time. Okay, so this is what happens when you have 4 bonds and 1 lone pair on a molecular geometry. And this one is called seesaw. Now, the reason that this particular bonding pair forms on the equatorial position is if you consider the bond angles between the two different locations. Here is a 120 and here is a 90. In Vesper theory, the point of the electron repulsion is to maximize the distance between your nearest electron. So the reason that the electron pair takes on a position in the equator is that the bond angle is greater and you can gain a 120-degree space, if you will, at that position. So we would form a seesaw whenever we add one pair of electrons as opposed to taking off one of the axial positions. All right, so if we progress on through the trigonal bipyramidal, we've already removed one pair of electrons. So if we go on and we represent what two pair of electrons placed would look like, we have our center and we have our, we had one lone pair here, and we're going to place another lone pair on, again, on the equator. So these are both on the same plane. These are on the equator, and you have remaining one bond pair on the center. Now this one is called T-shape. T-shaped. I know it looks a little bit odd here in my drawing, but again, remember I'm drawing this in one dimension, so it's kind of hard to represent. So whenever you have three things bonded and two lone pairs, you have T-shaped. If you go on and you then remove the third bond pair on the center and place it with another lone pair, this one becomes linear. Now remember, you are going to first represent it as being part of the electron domain geometry of triangular bipyramidal, and then you're going to call it linear for the molecular geometry. So this one is the same bond angle as a regular linear, but it has a different, it came from a different electron domain. For our last electron domain geometry, we have our 12 electrons on the center, and this one was in the octahedral family. Now, an octahedral has our center with our axial position, and then on our equator we have four evenly distributed. So these are all 90 degrees, and it doesn't matter which angle you look at, they're the same. You would think that you would have a lot of potential molecular geometries, but because they're all the same degree of angle, you have only two additional molecular geometries. So when you take away one of the bond angles, you end up with a molecular geometry called square pyramidal. And I need to draw in my non-bond domain. So in this case, we have our bond, our unshared pair of electrons, and then the rest very much in the shape of a square pyramid. If you go on and you remove an additional bond, you are left with what we call square planar. And you have your unshared electrons on the top and the bottom. And again, these have 90-degree angles. So these are the two molecular geometries for octahedral,